Definition number 2 is independent events. So if we're told two events are independent, it means the intersection can be determined by multiplying the two individual probabilities. So independent events means that the outcome of one has no impact on the other. So we think about things like tossing a coin, rolling a dice, all right? No impact on the other. Maybe taking shots at goal, or the chances of it raining today could depend upon whether it rained yesterday. Things like that probably aren't independent. So unless we're told independence applies, we should never assume it, unless it's one of those clear-cut ones where it's just obvious, rolling a dice, tossing a coin, where the events we say are memoryless, all right? So that's independent events. The next one is conditional probability. So conditional probability is where the outcome of one event can be affected by what has already happened, or what happened previously. So the probability of getting a goal with my next shot, given I missed the previous one, or the probability of it raining tomorrow, given it was sunny yesterday. So normally the key term, we often see a given in there, okay? Not always, but often. So if you see a given expression, A given B, probability of A intersection B over the probability of B. And don't forget that A given B is different to B given A. The probability of A happening given B has happened is different to the probability of B happening given A has happened. Okay, so just be very careful. So a couple of little examples here. Collingwood wins 80% of games on a weekend if they train well on Thursday. If they train well on 90% of Thursdays, find the probability. I think with any, I'll keep that for now. So they train well, don't train well. And it says they train well on 90% of Thursdays. So they train well 90% of the time, they train badly 10% of the time. And then depending upon they win or they lose, so I'm going to write win or don't win. Win or don't win, okay? If we train well, we win 80%. So that's 0.8, that's 0.2, all right? So what this probability here, okay, is, that's the probability of winning given they trained well. And the probability of winning given, the probability of not winning given, just get rid of that, they train well, okay? So those probabilities on this branch of my tree diagram are dependent upon what happened on the previous step. So that 0.8 and 0.2 are conditional probabilities. It's dependent upon them training well, all right? What's the rest of the question? Find the probability that in any given week they train well and win. So I need the probability of a train well and win, which if we just follow our branches across is 0.9 by 0.8, which is equal to 0.72. Or using my conditional probabilities, we know that probability of train well of winning given they train well is equal to the probability of winning and train well over the probability of train well. Therefore, the probability of win and train well is equal to win given train times the probability of train. Run out of room there. Win given train, we just decided was 0.8. The probability of training well was 0.9, and so we can see it's the same values. So we can use our formula, or we can just go straight to a tree diagram. What about Paul's? Probability of kicking more than 4 goals on a wet day is 0.3. Calculate. So again, there's only 2 events happening. So I'm going to go with, so kicking goals depends on the wet and dry, so we put the wet and dry first. So it's going to be wet 0.7 of the times, so it's not wet 0.3 of the times, and we kick more than 4. If it's wet, I kick more than 4 goals 0.3, which means I kick less than 4 goals 0.7. I kick more than 4 goals on a dry day 0.6, or on a not wet day. Actually, you can see there, I'll use 2 different notations there. So one of them, more than 4, the opposite is, the opposite is less than or equal to 4. But in this one here, I just put not more than 4. So you can, in fact, use either notation, but I guess in reality, I'm keen for us to get used to the not notation. All right, A. The probability it is dry and Paul doesn't kick more than. So the probability of not wet and doesn't kick more than 4. So find that on my tree diagram. Equals to 0.3 times, oops, I forgot to fill that in, 0.4, which is equal to 0.12. Okay. B, probability kicks more than 4 goals next game. So the probability of more than 4, well, there's 2 ways I can kick more than 4. It can be wet and kick more than 4, or it can be not wet and kick more than 4. So following my branches, wet and more than 4 is 0.7 by 0.3, or, which is a plus, not wet and more than 4 is 0.6, so we get 0.21 plus 0.18, which equals 0.39. Hopefully we've got room. C, the probability it was wet given Paul kicked more than 4. So probability of wet given more than 4. So if I go to my rule, that's the probability of wet and more than 4 over the probability of more than 4, which is equal to wet and more than 4. Where's that? Wet and more than 4 is 0.7 by 0.3. And the probability of more than 4 we just worked out, which was 0.39. So it's 0.21 over 0.39. Never leave decimal on decimal. So in reality, we multiply top and bottom by 100, and we end up with 21 on 39. All right, so just using our rule as we come across it. Finally, find the probability that in the next 3 throws of a coin, there are exactly 2 tails, given at least one is a tail. Right, so let's have a look at our, well, if we just do a quick, you'll soon get used to, so head, tail, head, tail, head, tail, head, tail. I think it's sometimes easier just to do a distribution. So we'll call the number of heads. Actually, we're not up to distribution yet, so we won't do that. So there's all my probability. So a head, head, head is equal to a half by half by half, which is 1/8. So each one of these is 1/8. Right, so I need the probability of 2 tails given at least 1 tail. So what's the probability in the next 3 throws there's 2 tails given there was at least 1 tail? So that's the same as the probability of 2 tails and more than 1 tail over the probability of more than 1 tail. All right, so let's have a look at the bottom one first. the probability of more than one tail. How many of all these combinations have more or have less, greater than or equal to one tail? And it's all of them except for the top one, isn't it? They all have at least one tail. So the probability of at least one tail is 7/8. Now let's have a look. I need the probability of two tails and at least one tail. So really it's just going to be two tails, isn't it? So how many have got two tails? So I've got a head, tail, 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 head, tail. I reckon that's it, isn't it? Head, 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 tail, head, tail, head, head, head. Oh, tail, tail, head. So there's three. Okay, which means then we get 3/8 times 8/7, cross out. So the probability of exactly two tails, given at least one is a tail, is 3/7. And the other way you can think about that in a conditional sense is the conditional part normally just changes the sample space, how many I've got to choose from. So I know from my counting up, there are three ways to get two tails, and the at least one tail means I know for a fact that it's not a head, head, head. Okay, which means there are still a total possible of 7 other ways. Yeah, so that's also a way we can sort of intuitively get our 3/7. All right, off we go.